All right, hello everybody. Sorry for last lecture's fire alarm. Stopped us right in the most exciting bit on LSTMs, so we'll try to catch up today. I hope we'll still be able to finish on time. LSTMs are super important, so we want to make sure we give them some time and gain some intuitions and that you ask some questions. We also had a video issue. Unfortunately, with the craziness, we kind of lost the audio of Tuesday's lecture and the video. So for those of you who are now only through video, the Stanford students can log into STPD. And for YouTube, we'll try to find another solution. But worst case, it'll just have to be last year's lecture and then check the slides for a diff. Are there any questions around organization for the class today? I hope you're all TensorFlowing away now. All right, awesome. So today we'll finish LSTMs and then we go into recursive neural network, a whole different kind of model family, though we'll see there are lots of connections also to recurrent neural nets that we've already covered. So this is where we ended on Tuesday, just when the fire alarm started. So we defined our LSTM, which is essentially another way to try to combat both vanishing and exploding gradient problems, but also keeping around longer term context and information from many previous time steps ago. And we again here have just a couple of standard neural network layers, 3 of them, the input, forget, and output gates with a sigmoid to be between 0 and 1, and a new memory cell, C tilde. And then we will compute the final memory cell, C, by basically multiplying the, again, this is the Hadamard product, just element-wise product. F is a vector, CT minus 1 is a vector. We multiply here, so if the forget gate is all 0, then we will ignore the CT minus 1, the cell from the previous time step. And if here we have now an independent input gate, so the input gate will define how much we're going to use from the intermediate memory cell. And then the final hidden state again has the option also to essentially take into consideration this input, again element-wise, or ignore parts of that input to make a final prediction. So usually we could have, for instance, a softmax classifier on this HT, but maybe we want to keep things around from previous time step, but we want to make them irrelevant for the actual classification of the current time step. So it's yet another tunable parameter that the model itself can tune and determine whether it's important or not. Yeah?
When do you choose between NH or sigmoid?
So here, the sigmoid is kind of the right choice because we want to either ignore inputs or smoothly go to really caring about them. So in this case, you almost always use the sigmoid. And here, theoretically, you could use ReLUs or other activation functions, in theory also sigmoid. Some of it is a bit of a black art. It just happens to optimize better with 10H. But also, if you have here ReLUs, then let's say your ReLU brings in a really, really large number, and now you actually have an input gate that wants to kind of ignore this input and put it at 0.01. But now because your ReLU is so large, your input doesn't have enough power anymore over actually modulating how much that input matters. And so it, in some sense, makes more sense here to keep around somewhat bounded activations. Does that make sense? All right, any other questions around the definition and equations? Yeah?
Can you give a little bit more information about how the input gate, which is the I, and the input modulation, or the block gate, which is C tilde T, like how they're actually interacting with each other?
how do I and C tilde interact with one another? I guess in general, the input gate basically can just modulate how much the current time step matters. And in some ways you could say, well, why have ht-1 here at all, for instance? But then you would hope that whatever this modified, I can still kind of overrule. So in some ways, because C tilde is in this formulation bounded between -1 and 1, it's still at the whims of the input gate to really be taken into consideration or not. But for instance, interesting enough, the input gate here is only between 0 and 1, right? So if this is negative, and unless I is almost all the way to 0, it will stay negative, for instance. So, but there's no, I don't know what else to say about how much they interact. I mean, you basically just have this simple product between numbers, and some are between 0 and 1, and others are between -1 and 1. But intuitively, it makes sense to basically allow the input to ignore all of what came at this time step here through C tilde. So basically now, this kind of model could, for instance, very easily keep a counter, a very simple counter of trying to, in your memory cells, keep around a lot of information. And also note here, yeah, so you apply the 10H after the CT. So just to get to the final hidden state. Cool. So now I think all the illustrations of LSTM units are a bit overwhelming and in many cases not super useful. At least not, I didn't find like they give me better intuition than the equations. But people are different, and so of all of them, some I think, yeah, but it depends on what you want to do. Basically here you define your simple multiplications, and you have nicely here overlaid where you have what kinds of nonlinearities and sigmoids and so on. So this is one such illustration. I find this one a little more useful, and this one, I guess, it abstracts away a lot. So you kind of see, all right, intuitively, your memory cell input comes. You have the input gate that will modulate how much that memory cell input matters. Your forget gate can determine how much of the recurrence do you ignore from the past, and how much do you want to forget from the past, and then your output gate can kind of determine what you actually use for classification at that time step. So those are just different illustrations, people trying different ways to make it a little more intuitive. I think it's one of the nice things and clear differentiators for the GRU is that we really do have that ability to say, at this time step, while I have some information that I think will matter later, I will not expose that to our softmax classifier, right? So that is one of the things that are more powerful. LSTMs, while very old, are currently very en vogue, and you've noticed this if you came to Project Advice Office Hour already. I suggest using LSTMs for a lot of tasks as a good first baseline. They're very powerful, just like the recurrent neural networks. You can start abstracting away and you just say, well, generally I have some input xt and some input ht-1, and then I will do a lot of stuff in here. So this will just be my LSTM unit. And now you can stack them just like you could stack the recurrent neural networks. You can have deep LSTMs at each time step. You can, and then unfold them also over time. And of course now each element, each LSTM unit itself has multiple deep layers or multiple layers inside of it also. Now, because you have all these weights, of course, you do need a lot of data. So you have to be very careful. If you have thousands, if your input dimensions will basically determine how many parameters you have, and now you have sort of 8x times input or hidden dimension squared many parameters. So if you have a 1,000-dimensional hidden state, 1,000-dimensional inputs, you all of a sudden have many millions of parameters in this model. And so ideally you'll have at least a couple of millions of training data points to train this kind of model. Yeah?
Can you explain which one of those gates actually contributes to vanishing gradients?
So the vanishing gradient problem here. So you have CT, so the question is which gate matters most here. And in general, the vanishing gradient problem can be fought if you can take derivatives and you don't multiply numbers that are smaller, much smaller than 1, with the inputs from the previous time step. So in this case here, we have clearly CT minus 1, for instance, and if f, this forget gate, which is really kind of 1 minus the forget gate, some people define it differently. You'll see a lot of slightly modified versions of this. Some people write 1 minus ft and so on, but the main idea, there are a lot of different LSTM variants too. I pick one here. A lot of people tried a lot of different variants of adding, additional Hadamard products here and there and inside here, and there's so-called peephole connections that will allow you to have access and so on. So there are a lot of different ones. In fact, there's a great paper by Jürgen Schmidt-Huber called LSTMs, a Search Space Odyssey, where he takes a bunch of standard benchmark data sets and compares like 20, 30 different LSTM variants on all these different ones, has lots of really great plots. It's actually a good paper to read if you want to also in your project kind of carefully compare a bunch of different models. But basically here is if f is close to 1, then you multiply here a number by 1 in order to get push your delta error signal through to the previous time step, and so that will basically make the gradient vanish much less than if f was close to 0. All right, so last year, and I mentioned this before, when I said deep learning is on the rise, even for machine translation, it was just in the second place in a WMT, which is a huge machine translation competition. It's a workshop on machine translation. It's international competition. Lots of top groups in translation compete in this workshop and have public data sets for training and development and then testing. And last year, the systems that were based on deep learning were still not the very best systems, and I had oracled that this will change, and indeed the competition results, all right, not from yesterday but from Monday, so I was hoping to get to this slide on Tuesday. So basically from this week, it's a little hard to read, but when you look at the top systems, you will see neural MT, and what that means in most cases is you'll have some kind of gigantic GRU or LSTM variant in the model. And now all the top entries here are basically neural machine translation models. And in general, if you get asked, when will deep learning work better? Well, if you have near infinite data, deep learning will eventually solve the problem one way or another. Better than most other traditional machine learning techniques. And machine translation is one of those areas where you have a lot of training data. Like you talk many gigabytes of training data. And it's a nice place also to apply monolingual data, of which of course you have like terabytes. You can download all of the internet as much as you can, collect in monolingual data, and you can improve machine translation models through that. And at the very bottom here, you have various phrase-based systems that kind of keep around the counts and do a bunch of clever feature engineering. And even those eventually started incorporating neural network models, but weren't able, if you still have mostly the phrase-based systems where you take the counts and you do all the alignment and stuff that I described, they're just not competitive anymore with the top neural systems. Now, there's some fun things that fall out of deep LSTMs also when you basically just look at what are the hidden states of the translation. And in general here, I'm cheating a little bit. So this is not necessarily just a single LSTM. This is going to be a more powerful deep LSTM. So let me just showcase really quickly what I mean here. So in general, we have our input vectors xt here and xt plus 1. And we plug those into some recurrent neural nets, and those were xt plus 2. This is our standard recurrent neural network. Now, we introduced deep ones, where now you can have connections, and at each time step actually have deeper layers. Now, what you'll often see is that people will just say, well, this whole block actually is an LSTM layer. And so internally, it has its own little layers, but people don't even draw those anymore. It's becoming more and more of a complex Lego block. People just accept that Lego block consists of 5 other Lego blocks that we all defined very carefully in the early classes, single layer neural nets put together with some Hadamard products, and that will be an LSTM layer. So when you have these neural machine translation models, you have 1,000 dimensions for each of the hidden layers. You have millions of parameters, and then you have times 8 for all the different blocks and matrices inside each of the parts of the LSTM, and then you have multiple of these times 1, 2, or 3, or even 4, where you have different layers of LSTM blocks. So these are pretty crazy beasts to train with huge number of parameters. Does this make sense? I know my handwriting is terrible. Basically, you can abstract away the more complex Lego block here, and then have kind of the LSTM building blocks where you have a bunch of separate layers and they all get put together. But in the end, they usually have an input x, some ht minus 1, or sorry, I guess this is ht, and this block will have some output ht plus 1. And that ht plus 1 will be the input to this next higher order LSTM block. Yeah?
So there are 2 outputs for each Lego block?
Are there 2 outputs for what?
So there are 2 outputs for each block. So one goes right and one goes left.
That's a great question. Are there 2 outputs per block? So each LSTM, if we can switch back to the slides, each LSTM has an HT, but now that HT is taken as an input both to the next time step as well as to the higher order LSTM at that time step. So basically, if you're looking at a higher order LSTM, you'll replace XT with HT from the lower layer. So you could introduce like superscripts, for instance. So you have, for the first LSTM block, you have H superscript 1 at time step t, and then you have H superscript 2 at time step t that takes as input the output of that layer. Cool. So now we can look at the vectors from the last time step of the last hidden layer, and we trained that with a machine translation model, a very deep LSTM that actually goes back to a lot of the very simple stuff that we described when we just had the RNNs, but instead of having a simple single linear layer, you have an LSTM block, and now you'll basically observe that some very interesting semantic patterns are falling out of this. So we can take this 1,000-dimensional vector now and apply PCA to it, and then look at a couple of sentences and the encoder that you get from them. And really cool stuff happens here. So for instance, Mary admires John, and Mary is in love with John, and Mary respects John, for instance. They're all close to one another. Or she was given a card by me in the garden versus in the garden I gave her a card, are also close to one another. So what you see here is that despite the word order being quite different, the different memory blocks and cells of the memory actually kept around the relevant information in a way that is somewhat invariant to the order of the words. So this is super exciting results. So really, machine translation is a great way to train models to just learn great representations for the language that you care, that you actually care about. It's almost as if it gives you a grounding and a way to understand, well, if I had these 2 sentences and one translator translated into this language and another translator in another book with a slightly different word, maybe it didn't give her a card, but a car or something, it learns that these are all very similar from the translation. So translation is a great supervision for learning good representations. And like I said, you could combine these in various kinds of ways. You can add new kinds of feedbacks and so on. And this is not, I'm not going to ever ask you to derive this and to really follow all the details, but I want to show you that now that you have these Lego blocks, it's a crazy exciting time right now, because everybody combines the Lego blocks in new kinds of ways, and you can have these input and forget gates, and you can modify them between different layers. And right now they're still very quickly, you can come up with new models and see if in real experiments on real data sets they actually improve outputs, and you can get some cool papers out. All right, so now we've basically covered recurrent neural networks. They just go from left to right, have a good time step. They're super exciting, a lot of ongoing work these days. The GRUs, or gated recurrent units, are much better than standard recurrent neural networks, and the LSTMs are often even better, but not always. So you really have to carefully compare the two. And again, this was sort of very advanced stuff. I'm not going to ask you to take a deep LSTM and derive all the gradients. It'll just be so many sub-indices. It's unpleasant. But really want you to gain intuition of how you can now creatively play around with these basic Lego blocks that we introduced, and you can combine them in new and creative ways. And you want to gain some intuition. Oh, my gradient vanishes because I multiply numbers here. Oh, if I add this gate, then maybe this won't happen as easily, right? So these kinds of high-level intuitions are what you should take out of the past lecture, but also what I'll talk about now, which is recursive neural networks. They're much simpler, so you should be able to follow it a little better, but we also don't have to go into all the details anymore. But if you still have questions, please do ask now and in office hours. Cool. All right. Any questions around recurrent neural nets? LSTMs, GRUs?
Why do you say that LSTMs might be better and jury's out? Like, what are some of the benchmarks that lead people to question?
Great question. So when is it better? It really depends on the paper, and there are a bunch of papers that compare them on machine translation, on summarization, on question answering, and so on. And it's not obvious that in all of these papers, one model always wins over the other. And there's no nice sort of theoretical justification of why one would always work better than the other, and there isn't in practice a clearer answer yet either.
So it's not a question of one of them causes the gradient to go up, and they do just fine in that respect. It's more application specific.
That's correct. So it's not like one has a huge theoretical problem and always, has exploding gradient problems, and the other one doesn't. They're both very powerful, very good models, and things that models that you ideally will run in a lot of your projects to compare. Yeah.
So how these techniques can work for other languages than English?
So the question is how.
More oriented like inflectional languages.
Sorry?
Inflectional languages.
So the question is, how would these models work in languages other than English, and maybe some with crazier morphology and very long words? So to give you an idea of what this means, basically German, for instance, has some very, very long words, and the words themselves capture a lot of information. So you might have a Dampfschifffahrtskapitän, which is like a captain of a boat that is powered by steam, right? And so in English you'd have multiple words describing that, and in German you can put that all together. So now if you start with just word vectors, you're going to be in trouble because there's so much information there, because you can kind of creatively combine new nouns into so-called compound nouns in German. You get a lot of rare words too that you might never see, and then it's harder to translate them. The same is actually true even for English when it comes to translating special nouns and company names and things like that. And so there are a couple of simple fixes, and in fact several of the papers here use this, which is one thing you can use as morphessor. So this is actually a way to split words with some very simple, based on some very simple metrics, into their morphemes, into the smaller parts, suffix, stems, prefixes, and compound nouns, separating out the nouns. And then it looks to the model very, very similar, and it's much easier to just take the standard LSTM. You can also go all the way hardcore to characters. There are actually some papers that recently came out, and you just translate from one character sequence to another character sequence. It's quite phenomenal, but that also works very well. you have to fiddle around a lot with the crazy learning dynamics, because now, the sentences aren't, at most 20, 30 words, but they're 20, 30 times 5 or 10 or so for the word lengths. But yeah, you can go with these kinds of models all the way down to characters. And then the language doesn't matter. It used to also be for Chinese, sort of the inverse problem, which is multiple separate characters might actually be put together as one word. And so maybe you would want to run first a way to do Chinese word segmentation, and then you translate the model. But these neural machine translation models and all the neural sort of sequence models, they can just take the characters and they figure out how to put words together. They're very powerful. Yeah.
Is there like a resource, like a paper on visualizing features from deep within LSTMs? Because I know there's been lots of work on visualizing the deep features from CNNs. Right. So is there a good paper on visualizing RNNs? There's one actually from this group, the NLP group at Stanford, Dan Jurafsky, and one of his PhD students. Do you remember the name of it? Or? I think it's visualizing recurrent neural networks or something. I can look it up after class. Do you have the title?
Justin Johnson. I know he worked on visualizing something. I don't know if it was with that group.
No, it's a different author. Cool. All right. So now let's talk about recursive neural networks. So generally, when we built our word vector spaces for single words, we found that they basically capture syntactic and semantic information, right? Parts of speech, like nouns, all cluster in one part of the space, and then as you zoom into the noun cluster, you see different semantic features and semantically related and similar nouns clustering together. So the vector of Germany would be closer to the vector of France than it would be to the vector of Monday, for instance. Now, of course, words never appear in isolation, and the question is, well, how do we represent longer phrases, like the country of my birth or the place where I was born? How should we represent the meaning of these longer phrases? Not just like all the context of everything we've read so far, but that phrase in isolation. And the simple answer can be, well, we also just want to map them into that same vector space that we had the words in. And ideally, they will now also capture syntactic and semantic information. So noun phrases that have, prepositional phrases inside of them, like the country of my birth. Of my birth is a prepositional phrase. The country of my birth is an overall noun phrase, which recursively has another noun phrase inside its prepositional attachment here. So ideally, those will also capture similar syntactic and semantic information. And so we've looked a lot at single word vector spaces in this class, and there are lots of other methods that we haven't gone into, traditional methods like Brown clustering. And certainly those kinds of vectors are useful as features to be plugged into any kind of machine learning model, neural network or not neural network. And then we also have in information retrieval and other fields document vectors. So the simplest one is just a bag of words vector, where every word that exists in a document gets a 1 every time I see that word in the document. And you have just a size of a vocabulary kind of document vector. Now, of course, the bag of words kind of representation will ignore word order and is not as ideal. You have to say, though, that if all you're trying to classify is the general topic of a document, you might not need to understand the whole sequence of all the words, right? If you just want to say, is this about sports or politics, you don't need to understand carefully how each word comes after one another. All you need to do is identify, well, does it mention Obama, does it mention the White House, and so on, or does it mention, touchdown and things like that. So for very simple information retrieval or document exploration and classification problems, you might not have to go all the way to a complex neural network model. Now, where it gets really interesting is when we try to describe phrases and sentences in a way that captures the word order as well as the complex semantics that we might see, such as negation or something, and you have maybe just a short tweet or a single sentence that you really want to carefully understand well. So that leads us to the question, how should we map phrases into a vector space? And one answer that will lead us to recursive neural networks is to use the principle of compositionality, which is a really interesting, very powerful principle, and in our case, it will state that the meaning vector of a sentence is determined by 1, the meaning of its words, and we already have nice word vectors for those. And again, these are just visualized in 2D. We know already they're usually 50 or higher dimensional. And 2 are the rules that are used to combine them. So in recurrent neural networks, we just said, well, we'll always take one word at a time, and we compute a context vector that just captures everything from the left that we read up until that time point. But maybe we want to have representations for all the syntactically plausible phrases by themselves. So maybe we want a representation for my birth, because I could replace the country of my birth with like the country of my choice, or something like that. And so maybe we want to be able to understand how we could replace this one in the rest of the phrase. And so the country is a proper noun phrase by itself. Of my birth in grammatical analysis is a prepositional phrase. And so we might want to change the order in which we're combining words to always try to keep around a syntactically plausible or grammatically plausible phrase. And then ideally that representation will still end up close in meaning to the phrases that are similar. So the country of my birth should ideally be similar to the place where I was born. And so the models in this section will actually allow us to jointly learn these parse trees, these grammatical analyses, as well as the compositional vector representations that represent ideally syntax and semantic information. So in sentence parsing, what would we want? Well, this is a very sort of fundamental task. A lot of folks in NLP have worked on parsing for many decades. And so just to give you a little bit of an idea, again, we could have multiple lectures just on parsing. In fact, you can have entire semesters on different theories, linguistic theories, underlying parsing algorithms that the parsing algorithms try to capture. So I took a year and a half of just syntax theories when I was an undergrad. I loved it at the time. It was super interesting because it's basically trying to capture all the complexities of language, and it really makes you appreciate how complex language is. And then depending on how far you go, you even go into places where normal speakers of the language don't even know anymore what you're talking about. But you're talking about their language and you're just understanding it very, very deeply. So for linguistics, this is a super interesting area. Now, we'll get to that later. It's a question whether we need it for artificially intelligent algorithms to fulfill certain tasks and get certain accuracies. But if our interest is the actual study of language itself, it's a very interesting formalism. All right, so if we try to do parsing and syntactic analysis here, the parser should understand that the cat is a proper noun phrase. You just added a so-called determiner here, like the. You combine it with a noun, you get a noun phrase. Similar with the mat. On the mat is a prepositional phrase, and in syntactic theory now, we could create another grammatically correct structure by replacing this PP or prepositional phrase with any other kind of prepositional phrase. Now, to sit on the mat or sat on the mat is a verb phrase, and overall this is a sentence. So this is the standard parsing task that gives us this discrete tree structure, essentially a grammatical analysis of which words go together to form syntactically plausible phrases. And now what we want is, of course, not just this discrete structure, but also vectors at each node in this tree. And this tree, again, it can be very different for every different sentence, right? Different sentences will have different trees. And so maybe it makes sense to step back and ask us first, do we really need to learn the structure? So we could, for instance, go and just say the country of my birth. Instead of finding the tree structure first, we could just go from left to right, and maybe we'll end up with some vector too. And depending on what the training data is, maybe it will be able to capture everything that we want. Of course, the tricky bit here, as you'll see, is that this structure will not give you a vector for just my birth at any given moment in time, right? It will only give you this vector here, which captures the country of my birth, but not my birth by itself. And so, you can get very quickly into very long conversations and discussions about the true nature of cognition and the brain and language by itself and so on. And you can certainly argue that they're cognitively debatable. Do we really form internally in our brain little tree structures? one thing that's clear is that recursion is very helpful in describing natural language. Right? If we want to say, is this a syntactically, grammatically plausible phrase or not, then it helps us to know that this is a noun phrase or verb phrase, and I can replace this verb phrase with another verb phrase, and it's still a good English sentence. So again, for describing language, this is certainly very helpful. And it can also be helpful to try to identify and sort of clearly specify certain disambiguations. So this one is a super interesting problem, so-called the PP attachment problem, or the prepositional phrase disambiguation. There are different words for it, but basically the big question here is how to interpret the following sentence. He eats spaghetti with a spoon versus he eats spaghetti with meat. Right? Intuitively, for us it's very obvious. Well, if I eat spaghetti with meat, then the with meat PP, the prepositional phrase of with meat, modifies what kind of spaghetti I'm eating. But he eats spaghetti with a spoon. Now, with a spoon is also a prepositional attachment phrase, but it actually modifies how I eat the spaghetti. And so if you want to describe that in a proper formalist way, this is a very powerful method to do so. Basically, you have these trees, and now you say this PP attaches to this noun phrase, whereas this PP attaches to the verb phrase. And so for a lot of linguists and a lot of even NLP systems, for a long time we assumed we first have to understand the syntactic structure, and then we can get to the semantic structure and actually understand what the meaning is really about. Again, cognitively debatable, but certainly helpful for different tasks. Are there any questions around this? I know we haven't really introduced all these tree structures, and these are personal pronouns, and they're different types of classes for verbs, so don't worry if you don't fully appreciate and understand those tree structures. But intuitively, they basically just capture the grammatical structure, and they're one-way grammatical formalism. Cool. All right. So now the question is this recursion helpful? It can be in a couple of different scenarios. So for instance, if you try to refer to specific phrases, not just specific moments in time in your time series. So you might say, John and Jane went to a big festival, they enjoyed the trip and the music there. Now you might want to say, who's they? And you want to refer to just John and Jane. Or you might say, what's the trip? And if you want to refer to it only in the sentence, it's just went to a big festival. And you can go to this festival without John and Jane. So you might not want to include them in your current context, which again a recurrent neural network would do. And you can even say, what does there mean? And then that's the big festival. But there's only the big festival, or a big festival. It's not the entire sentence from left to right. And you might want to have actual representations, independent representations of these phrases, depending on what systems you like to build. Now, the labeling might also sometimes be a little less clear if you only have a label from left to right, or only one for a single word. So you might, for instance, say, I like the bright screen, but not the buggy slow keyboard of the phone. It was a pain to type with, or it was nice to look at. So now you want to refer to it. Maybe this it should refer to the bright screen, and this it should refer to the buggy slow keyboard, and not just to keyboard by itself. So this is an interesting task of so-called coreference resolution, or when it's a specific anaphora here, like it, basically a pronoun that you want to refer it here to the buggy slow keyboard. And in some cases, you might also just say you run experiments, and you want to just say, well, I don't care really which model you like better. You should just run an experiment, and you can compare different models. And sometimes, for instance, for sentiment analysis, up until we put out our dynamic memory network paper, the best model in terms of just pure accuracy on the Stanford Sentiment Tree Bank, which is a very commonly used benchmark data set for sentiment, the best performance used to be models based on models that use these grammatical tree structures. And now they were overtaken again, and who knows, maybe a next kind of modification of tree structured LSTMs or something will improve it again. So it's basically still up to debate. In some ways, if you're a linguist, you will love recursive applications because they really help you carefully describe language in a very good formal way. If you just want to get good accuracy, maybe you won't need it. So let's assume for some of our tasks they're useful and we really do want to use them. Now let's see how we would actually compute these tree structures and the representations for specific phrases in a grammatically plausible way. We'll use recursive neural networks for this task. And the basic definition of these is as follows. You basically just have, again, two inputs. Originally, they will just be words, and later on, they'll be phrase vectors. And you'll have two outputs. The semantic representation of the two nodes that we merge, and maybe on top of that, again, is a standard score. So none of this will be too big of a surprise. This is, again, our standard neural network, single neural network layer. Here we actually put the W into one matrix. So again, this could be seen as two blocks. One block that you multiply with C1 plus another block that you multiply with C2. This is what I described in the previous lecture. And we basically just have a single linear layer here to compute the parent. And then we have our standard score, linear score, to just say, well, these two should really go together. So if this score is high, we want to combine these two words for sure. Are there any questions around the formulation? So maybe we can do a quick check if we're all on the same page. So let's say our W here, we can split into two matrices. So this is C1 and C2, and this is our matrix multiplication. Right? So this is just part of our F of W plus B. Now, how could we rewrite this? And again, this is just this whole thing here is one W. How could we rewrite this if we wanted to separate out W1, W2? And have the formulation we have here C2 and here C1.
W1, C1.
That's right. Plus?
W.
That's right. Right. So again, just straight up linear algebra. We'll often use this formulation. It looks a little nicer for recursive ones. All right. All right, so now let's, can we switch back to the slides? So now the main reason we call them here recursive is that we use the same W parameters at all the nodes of the tree. And now you will very often hear the confusion between recurrent and recursive neural nets. Recurrent ones, the way they're currently defined, will be just chains that go from left to right. At each time step, you add one word. And so in that sense, recurrent ones are actually special cases of recursive ones, because chains are special types of trees in graph theory. And so in some ways, you can basically just assume that a lot of the stuff will follow, and sometimes the recursive one falls back and is like the special case of a recursive tree structure is just a left to right structure. I see a little bit of confusion, so let me just show you what I mean. So we could have, for instance, a tree structure that just keeps combining things from left to right, right? And now, if you assumed you had modulo sort of a hidden a start state. So now this is basically very similar to saying, well, I first combine this here, and you should have of course arrows. Now this is very similar to saying, well, I just basically go here, right? So just basically fold these down, and then you see that this is just a special type of tree. Main difference here is how we deal with the starting point being an input as well. All right. Cool. All right. So now let's say we had a trained model that gave us good scores for when we actually think two words should go together, and or high scores, and low scores when they don't. So now the simplest way, and the only way we're really going to look at it in this class, is with a greedy tree search. We'll basically here have this neural network, the same W weights, and we'll apply this for every possible combination of two words. And we would just say, all right, now the cat is a very obvious noun phrase. Cat sat doesn't seem like a plausible phrase. Neither sat on or on the, but the mat, again, obvious noun phrase, so gets a high score. And now what we could do is say, well, let's just make some discrete decisions and say, let's combine the two words with the highest score, and then take the output of that model and apply it to that same exact neural network again. And again, the weights here are all shared, same W at every node. And then we can again compute a candidate here and say, all right, the cat sat. How likely is now the combination of these two words represented as a single vector again with the verb sat? And now here, the largest, the cat sat is actually not an unreasonable phrase, so you might think, all right, that's still a reasonably high score, but the mat was a very obvious noun phrase, so we'll combine those two words again, and then again compute a candidate representation for what comes afterwards, for all possible combinations if we make these greedy kind of decisions. So now on the mat is essentially a very nice prepositional phrase, so it gets again the highest score, and we basically build up this tree structure like that. All right, now we can define the score of the entire tree as just the sum of all the scores of all the decisions that we made to arrive at this tree. And so here x will actually be our input sentence, and y is the tree structure. And so you have a bunch of nodes in that tree, and each node had this kind of score, and we're just summing them up. Now this one is where it gets a little interesting. This is similar to our max margin that we had before, where we had 1 minus the, or max of 0, comma, 1 minus the score of the good window plus the score of the bad window. But it's a little more complex because we have now various different gradations of difference and gradations of goodness, or essentially the loss here in penalization term. So let's walk through this slowly. I don't think you'll have to really derive this or use this yourself, though we will have in problem set 3 recursive neural networks, but you won't have to train this to actually find the tree structures. In most cases, we will assume the tree structure will be given to us. So this is a max margin training framework to try to find a recursive neural network that gives us the right grammatical analysis, the right tree structure for a sentence. xi is, we have basically here summing over all the sentences and training trees in our corpus, our training corpus. So we have a bunch of different sentences, and each sentence has a ground truth tree yi. So this is our training corpus, a bunch of xi's, yi's, and yi is some formulation of this tree. And now what we want to do is we want to maximize the score, and the score again of the whole tree is just the sum of the scores at each of the nodes, of all the nodes. And we want to maximize the score for our current sentence xi and its correct tree yi. And now, what is this monster here? So basically, what we're going to do is we're going to try to find the maximum of all possible trees a of xi. So a of xi is just a large set of all possible trees that you might create from that sentence. And basically each of these will be some distance delta away from the actual correct tree. And you can count that by basically how many of the words, how many of the right decisions that you make to get to this tree. And then once we found that tree, we want to actually lower its scores, because unless it's the exact same tree as yi, so if the maximum currently scoring tree of all our randomly initialized parameters, unless it's actually the exact same tree, we want to penalize all its scores, because we messed up. The algorithm messed up in finding the right tree structure still, in terms of the scores here. And so once the highest scoring tree, y, is actually the same tree as yi, well, then these two will cancel out, and delta here will actually be 0, because the difference between yi and yi is 0. So you made all the same decisions, and then you're basically done with trying to optimize that tree. Now, of course, a of x, this set, is exponential. It is a very, very large number of trees. You have millions of possible trees, even for sentences of just, length 40 or so. And so really what we're going to do here usually is a smarter search, often a beam search with a chart that tries to find the best tree. So far, the structure here that I described was just a greedy version. It's the simplest way. But maybe you make a mistake internally here and you want to be able to recover, so you might want to keep around multiple possible choices that you may have made. And so that will be basically one way to do this is in a beam search. No, don't worry if you're not familiar with that that much. You're not going to have to implement beam searches or charts. Any high-level questions around that equation, though? So basically, if you make just one incorrect choice here between y and yi, then delta will be 1. But if you have a completely wrong tree where you made a bunch of wrong decisions, then your delta will be much larger, and then you're also going to try to penalize all these incorrect decisions even more. And so once you actually have y be the correct tree that is exactly yi, then it will also be correct up to a margin to the next highest scoring tree that isn't correct. And it will be nicely pushed away all the incorrect decisions. All right, so now how do we train this? Well, really, it'll be mostly backpropagation, as we've already derived it. We'll see these two equations if we implement this from scratch in NumPy again. But there are three major differences that sort of conceptually you might stumble over. So the first one is that we'll actually sum up all the derivatives of w from all the different nodes, somewhat similar to what we've done in the recurrent neural networks. You might see the splitting of the derivatives at each node based on that difference of notation. And you basically can add different error messages from all the parent nodes that you're getting and the node itself. And so a lot of this is actually quite similar to what you've seen with recurrent neural nets, where we had the error signal at each node and we basically sum them up going from right to left. Here you just happen to go in this tree structure. So let's just quickly gain some intuition for why you can actually assume that there are different W's at each node. So let's say we had the simplest kind of model here. This is actually a recurrent one, and if you just now derived the derivative of this function, so f again, just nonlinearity, we could assume w here for now is just a scalar, and we have this very simple function. You take derivatives and you just apply the chain rule in its simplest form. You're going to get to this equation. If you take separate derivatives of each occurrence here and you assume, well, maybe this is w2 and this is w1, and then you actually sum them up and you apply the simple chain rule to that, you end up with this. And now if you basically drop the indices, you realize, oh, they're actually the same. That's just like very simple. Just to gain some intuition. Because I use this equation here a lot, I just want to make it clear that generally as you get an error message from your parent and you send it to the children, you'll end up at some point with a delta error signal here that basically is part coming or going to the left child and part to the right child. So this is usually a notation that you will see. And now at each node, and I'll show you some like code. It almost looks like pseudocode, but it's actually real code. Intuitively here, you might have a score. You do have a score at every node of the tree, as well as from the parents. And so basically what that means is in forward propagation, you compute these scores, but then you continue using the parent in the next computation higher up. And so the total error messages that will arrive at each node that is internal to the tree will be one where you have your score sending you a delta message and your parent sending you a delta message or an error signal. And you'll basically sum them up. And it's a good exercise to gain some intuition of why mathematically you end up just summing them up. So we got asked for some nice code. So here's some very simple recursive neural network code. We'll assume here we have rectified linear units in our tree structure. So our hidden node here is going to be just a computation of W times horizontal, in this case, stack of the left node and the right node plus our bias term. So there's straight up simple neural net, and our nonlinearity followed by from this simple inner product, matrix vector product, is just our rectified linear unit. Now instead of linear score, we can also use a softmax at every node and actually classify every single node in this tree. So let's use the simple softmax here. This is a trick that I think it'll be good to derive of why you can do this mathematically, but you also always want to basically subtract the maximum. It'll give you the same output, but because we're going to exponentiate this, it'll help you numerically to stay much more stable. So the real question here, I kind of went over it quickly, is why is it the same if you take out a linear value from all your elements before you apply the softmax? And proving to yourself that that is the same is a good exercise. So then here we just have our softmax, basically sum up probabilities at that node in the tree to be 1. And again here we just assumed we know what each node is basically its own little class, and just proper object-oriented programming, each node has a left child and a right child. And that's one simple way in object-oriented programming to get to define a tree structure. And now I mentioned these two equations and again how important they are, and we'll see them here again directly in the code, modulo maybe some transposes depending on what we use as the vectors. But so the softmax gradient that you already derived will give us a delta at that node. You basically have your y minus your y hat minus y. This is basically the delta coming from here. So you have your softmax weights times transposed to have the final error message that comes into this node. And then here you have your f prime. So I'm skipping about over this one. Basically, if you, but I shouldn't, if you have, if you're at the top node of the tree, then you might not have a parent. Right, if you're at the root of the tree. But once you do have your internal child, you will basically get the delta from your current softmax at that node plus the error that was coming in from your parent. And now we will have our f prime of z, this one right here. And in the case of the rectified linear unit, that is just a simple 1 or 0, whether you're in the linear regime of your rectified linear unit or you're in the 0 regime. Now this one is an interesting special case. If that final node is actually a word vector, then you will basically add here in your lookup table or your word vectors, maybe your large word vector matrix, you add that delta error message into the word vector. So again, those are part of your training. And this is also true for all your recurrent neural networks. And now this one is where all the juicy bit is and all the interesting stuff. So here, our derivative of W, well, it's the outer product, just like we have here, the outer product between delta and the activations. So the activations in this case are just the concatenations of your left and your right children. So basically, you see exactly this equation here in the code here, and you basically sum up at each node, you add more to the derivatives of your W. Deltas derivatives with respect to B are just the delta messages, as we've seen in one of the early lectures. And now we're basically going to split up and send the error signal down. So here you'll see the W transposed, this W times delta. And this part here we will only do once we actually arrive at those nodes. So that will come later here. And there you go. And that basically now you can run and recursively apply the backpropagation function with the new delta, the error message that now gets sent to the left child, and one that gets sent to the right child. So this last part here is exactly the splitting up of these delta messages. So intuitively here you have again one of these computational flow graphs. You go up the tree to compute all your activations, and then you go back down the tree in the reverse order. Are there any questions around backpropagation through structure? All right. So, as before, do you have one?
So I'm a little unclear. If you go back to the code, how do you control the structure of the tree?
How do you control the structure of the tree? So, basically, you assume for now that you just defined an object-oriented setting here where you have nodes, and each node is a standard sort of object-oriented programming type object. And it has defined a child, a link to its child on the left or its child on the right.
I guess my question is, how do you know the structure?
Oh, great question. So how do you know the tree structure? So this backpropagation through structure always assumes you have a tree. So either you, and in most cases, and in the case of your problem set 3, you will be given a parsed tree. Well, we take the, in our case, Stanford parser, actually happens to also be one of the best parsers in the world, and the Stanford parser will give us what the tree structure is for every sentence. And then we actually, for sentiment analysis, took those tree structures and labeled all the nodes and all the phrases in the tree to really understand, oh, now you add negation, now it should change in its sentiment. So it's a very nice and intuitive kind of data set and labeling process. And so in your problem sets, you will just assume the tree structure is given. Now, if you actually try to find the tree structure, you would use this kind of model where you trained it and then you will use a simple search procedure. Who here has taken 221, the standard AI class? Okay, so like roughly 1/3 or so of you. So you'll have looked at a lot of different like sort of traditional AI search methods like A-star search and so on. So these kinds of beam searches and other kinds of searches are kind of a traditional part of AI. So yeah, you'll use those kinds of search methods to find what the right tree is. The simplest one is this kind of greedy structure where you just say, well, what's currently the best method, currently the best choice, and then I'll just put the tree together this way.
Well, I mean, I guess beam search doesn't, but like A-star needs a heuristic that is consistent in all of that jazz, right? So that it actually converges. Beam search is not guaranteed to converge.
You cannot do nice dynamic programming with these recursive neural networks, largely because you actually have these continuous vectors and you can't make the kinds of independence assumptions that you could do if you had discrete choices like, oh, this is just a noun phrase. But really, and that noun phrase is locally the best one, and because it's locally the best one, it will be globally the best one. You cannot make these assumptions. You might have the highest score for these 3 words, but then because of the continuous vector representations, the highest score for the subtree might not mean that that's also going to be the best one for the overall tree. So all you can do is beam search. And again, don't worry if this went over your head a little bit. Ideally, you've taken 221, but you don't need this for the projects or the programming assignments. Cool. So now we'll basically, again, have forward prop, back prop through structure in this case. We'll get our gradients. We already talked about AdaGrad. It's a very nice method to basically have a different learning rate based on the past gradients squared of all the previous time steps. That will update our different vectors and matrices. And because you have actually technically here a non-continuous objective function, you use a subgradient. Again, we're not going to go into too many details in this class about that. Now, you can actually get reasonably good results if you just take a single W matrix at every node of the tree. But it's also kind of crazy to assume, just like with recurrent neural networks, that one single W matrix could capture all the complexities of all the different combinations for adjectives and noun phrases and verbs and prepositions and so on. And it's a little much to ask such a simple function, right? Concatenating 2 vectors, multiplying them with a single matrix W, having these simple linear transformations and adding a bias term to capture all the complexity of language. And so one of the extensions of recursive neural networks is to syntactically untie the weights and actually use different W's depending on what kinds of phrases and words you're actually combining. And so on a very intuitive level, the standard recursive neural network will use the same W at every node. But because we actually often use a parser that tells us not just what the tree structure is, but also what kinds of phrases we have. So this might be a noun phrase, and this might be a verb phrase, or an adjective phrase, and so on. We can actually use different W's depending on what category. So capital letters here are categories, and the small letters are the vectors. And so we can actually combine these 2 vectors differently because one is in category B and the second one is in category C. And again, yeah, we're sort of now arrived in slightly more advanced territory. But intuitively, we're using the same kinds of building blocks that we've used before. Yeah?
So if we're treating recursive neural network or recurrent neural network as a special type of recursive neural network, does that, because in traditional RNN we only have one set of weights, and I always wanted to ask this question, why don't we use different weights for different time steps? So wouldn't this be kind of like an example of using like different weights for different time steps?
Yeah, so the question is this an example of, or I guess not quite an example, but this is an interesting analogy to using different weights at different time steps in a recurrent neural network. And I think you're absolutely right. I'm going to say that there's probably going to be a paper this or next year that will try that, because now, this is again, side note, don't worry if you don't follow what I'm saying right now, but batch normalization, for instance, you start to collect training data that is different at each time step. So I think a logical next step is to go back and say, well, why don't we have a different W1, W2, W3 for the beginning of recurrent neural networks? The problem is, of course, what if you hit a test sequence that is longer than a training sequence, and then you might just say, well, I have W1 to N, and N+1 has all shared the same W. Again, you kind of fall back to a recurrent neural network. I think it's an interesting research question. Somebody should definitely try it. It would be a great project too. Cool. All right. Now, one of the problems when we try to find the tree structure is actually that having a matrix product, a matrix vector product, at each potential combination of phrases is actually very complex. And so what we end up often doing is to take a very simple model that's just based on counts. It's called a PCFG, probabilistic context free grammar. Again, don't worry if you not follow this. And that will give us a bunch of candidates, like 200 or so. And then we'll use the more powerful recursive neural network that understands the semantics and has complex vector representations to just basically prune out all the unlikely candidates and give us one that makes most sense based on this simple sort of pre-processing step. Now, these are also models that have all been kind of evaluated and invented in their most basic forms in the early 90s. Pollack in 1990 invented recursive auto-associative memories. So these are essentially autoencoders that are recursive. They try to recover at each time step what came into that time step. Turns out to, in my own experiments, not always be the most useful objective function to try to capture meaning very well, but it's a good regularization to not try to overfit to your supervised objective at each node. And then, of course, whenever you do something in deep learning, Jeff Hinton will have had some idea similar to what you're doing also in the early 90s. So yeah, lots of folks have tried this, and there are some cases where recursion makes even more sense. So if you would have, for instance, programming languages too, and you try to understand, well, this part now modifies that exact region in that specific window. If you have, for instance, for loops or something, you want to now have a for loop and a sort of abstract syntax tree. In programming languages, it also makes a lot of sense. Or different logical operators where you might say, I want to negate something, but I want to negate it exactly until right here. And you have parentheses, and whenever you have complex sort of Lisp type programs, for instance, it makes sense to think of them as trees. And like I mentioned, parsing by itself is also a very large field in NLP. A lot of very smart people have worked on parsing. And for a while, these recursive neural networks were quite accurate, and we actually shipped them in the Stanford parser. They're a little faster than some of the traditional methods, but were more accurate. But a lot of back and forth actually happened in the last couple of years, and I think currently a neural network is again the top model to understand these tree structures. I think more importantly, we can analyze what's actually being learned in these recursive neural networks, and we find some nice notions that linguists had invented, and now these RNNs, or because RNN is now somewhat ambiguous, I'm going to call these sometimes RVNNs for recursive neural networks versus recurrent neural networks. Again, one is a special type of the other, so it doesn't matter too much, but all right, side note end. Basically here, this syntactically untied recursive neural network basically had these different W matrices for the different vectors, right? And again, coming back to this idea that you multiply the two, you can see here the two blocks of W that multiply with a determiner and the other one that multiplies with the noun. So if I say the cat or a cat, what this basically learned is that it doesn't really matter that much. It's going to be a noun phrase regardless. And in terms of the meaning, you care much more about the noun than you care about the determiner. Is it this cat, that cat, a cat, the cat, and so on? None of that matters. The cat is really what matters. And this is exactly what this model learned. The weights here that are multiplied with the noun are actually much larger than those weights that are multiplied with the determiner. And intuitively, in linguistic theories, people have a notion of so-called head words, the word that matters more in the combination of a phrase. And so there are lots of interesting linguistic theories of people who really understand and analyze language. And it's kind of cool that the model itself learned similar patterns. So for instance, in verb phrase and noun phrases, often when you combine a verb phrase and a noun phrase, it ends up being a verb phrase. And so the verb here matters, again, more than the noun phrase. We can also look at semantic similarities and syntactic similarities by looking at nearest neighbors. So we embed a bunch of sentences, and this is a much smaller data set than what we saw for machine translation, but some similar patterns are falling out when you use recursive neural networks. So here we take a bunch of sentences, a couple thousand, and we basically project them all through a recursive neural network into a vector space, and then we look at nearest neighbors in that 50 or 100 dimensional space. And when we look at the nearest neighbors, these are the sentences that fall out for here three picked examples. So all the figures are adjusted for seasonal variations. The closest neighbors to that are all the numbers are adjusted for seasonal fluctuations. So basically just replaced figures and numbers and variations and fluctuations, two synonyms in this word vector space. And all the figures are adjusted to remove usual seasonal patterns as the next closest one, which is kind of interesting because now it basically adjusts this whole verb phrase to remove usual seasonal patterns versus adjusting for seasonal fluctuations. Sorry, I guess adjusted and adjusted are the same here, and here you're adjusting, removing usual seasonal patterns, and here you adjust just for seasonal fluctuations. So now here you have a couple of organizations, and you basically see that it captures, again, the syntax, similar to our word vectors, where we captured, first this is a noun, but then let's zoom into the noun, you have similar semantic information too. So Nightritter wouldn't comment on the offer is close to Harsco declined to say what country placed the order, which is, the next closest nearest neighbor in our high dimensional embedding space is Coastal wouldn't disclose the terms. So you can kind of see, some organization, some kind of negation can be wouldn't or decline, so different ways, and then commenting, saying, disclosing something of some financial nature. And here are other ones like sales grew or rose or surged and so on from some amount to some other amount. And very interestingly also we can look at exactly this disambiguation case and see if our word vectors and distributed representations for the phrases help us to do this disambiguation. This is not really a proper experiment because it's a tiny training set and a tiny test set, but we can see if this happens at all if we add these sentences to our training set. So here we have training sentences, he eats spaghetti with a fork, or she eats spaghetti with pork. And then the test sentences are he eats spaghetti with a spoon and he eats spaghetti with meat. So ideally, because the distributed vector representations for pork and meat are similar, and likewise spoon and fork are similar, a neural network model can kind of make that cognitive leap and say, well, this should be similar to this one and not the other way around, whereas a model that would just traditionally use traditional machine learning and take counts of words that are completely independent, they're just one-hot vectors for some kind of counting, wouldn't do very well. And that's what we did observe here. So the compositional vector grammar, which has a recursive neural network inside, did correctly put the with meat prepositional phrase close to or attached to the noun phrase. All right, now I mentioned that we can have the softmax layers too. I showed you the code for the softmax. So we can take each node in a tree, apply a softmax classifier to it, and classify also what that node should be in terms of its class. And what was really fun to see in 2011, this was the first paper of my thesis in 2011, was that instead of taking word vectors, we can also take vectors that represent little regions of images, so-called superpixels. And then we applied the same principle of compositionality and said, well, the meaning of a whole region of an image might also come from smaller regions of the image and how they're combined. And so we used this idea and basically learned how to combine different areas of images and got some really nice results also where it's the exact same model that we used for parsing sentences, but now we parsed images, little regions of images. You have a W vector here, and you basically combine them with these scores. And for some time, it was actually a really, really accurate model for basically classifying and segmenting whole scenes. So these recursive neural networks, just like convolutional neural networks, can be very generalizable between different modalities. And that's one of the reasons why I care more about the methods and less about the application. And you can have projects in a variety of different fields, because the power of these models is really that they're applicable to everything. All right, so next week we'll talk about some more variants of recursive neural networks, and then we'll get to convolutional ones and some other ones.